Welcome to this new radio design series. Today we're going to talk about bandpass filters, something called Q or quality factor, and matching networks. Actually, in part one, which is what you're watching now, we're just going to give kind of an overview, and then part two goes into a lot more depth and covers the Q and matching networks. Here's the outline for episode 1 of the radio design series. We're going to start by talking about transmitters and receivers to set the big picture. Then we'll delve down into the circuits level, doing impedances, Ohms Law, and something called voltage dividers, which are central to filters themselves, which we'll cover in terms of low pass and band pass. And then, if you're up for it, go for part 2, which will actually prepare you to design things. So what is this good for? Well, radio design. And over here on the left, you can see a ham radio, one that I have. And just to the right of it here, this middle part, this is a radio that I designed and built. So this is a completely homebrew one that I did many, many years ago. And over here on the right-hand side is a fully integrated transceiver down here at the bottom that's mounted on a small circuit board and was part of a NASA research project that the team that I was involved with was in. So what we're going to be covering today comes from a course that was taught at Kansas State University, and it will basically tell you how all of those things work. Doesn't matter what the year of design of the radio is or anything else. This is timeless information. So what you're seeing on this screen is a picture on the right over here of a radio designed and built by one of the students in our courses. And we've built literally hundreds of these over the years. They are designed from scratch by students, starting with a block diagram of a super het receiver that we can see down here. And you can notice that there are bandpass filters throughout this. So there's one over here on the left, and then there's one to the right of the low noise amplifier. There are bandpass filters in the intermediate frequency processing and so forth. This other screen up here, I'm not going to talk through that, but this gives you an example of the kind of things we do at a university course. Notice this is a senior level university class. So what we're going to cover today in this part 1 is fairly high level and doesn't require a lot of mathematical background. Students obviously have that, and so they'll get kind of a deeper knowledge of what's going on. But I'm hoping that in today's video, we can explain a lot of what happens in a bandpass filter design. All right, so outline of this video. Before we jump into bandpass filters, we're going to step back and look at the big picture. In particular, transmitters and receivers. After that, we will go into impedances, Ohms Law, and voltage dividers. And then we'll talk about how the filters themselves are designed. Big picture. How does radio work? Well, you start with a sine wave voltage source at a fairly high frequency. High is relative and has changed over the years, but megahertz to gigahertz or above. And this voltage source puts charges on this antenna element at the top that are, say, positive at a given instant in time, and negative charges on the bottom. And what that does is it creates an electric field from the top to the bottom here, from the top element to the bottom element. As the voltage changes, those charges are moving in and out of these wires, and that creates currents. And what do those currents do? They create magnetic fields, here denoted as H, around the wire. So you have an electric field here running sort of vertically, and then you have a magnetic field perpendicular to that. And what happens to make radio work, as figured out by Maxwell and then demonstrated by Hertz long, long ago, is once these electric and magnetic fields, which are time varying, are created near the antenna, according to Maxwell's equations, according to the structure of the universe, how things really work, they will regenerate themselves and no longer be dependent on the source, and they will propagate away from that source. Now, over on the right-hand side, we can see a receiver, and those fields come near the antenna, and there are various ways to view this. You can view it in terms of magnetic fields or electric fields. Here, it's a wire antenna, And so I'm going to assume it's an electric field that is causing things to happen. It's really both. But the electric field pushes and pulls on the electrons in the metal wires here, causing current to flow through. This represents the input impedance of the receiver, some resistance, and that develops a voltage across it. So it is that voltage that then needs to be amplified. Now, looking at the big picture from a circuits level, here we have an abstract view of a transmitter on the left and a receiver on the right. Transmitter does what we just said. It creates the voltages, carrying information. That's the modulation term here. We won't talk about that today. But that then creates the signal, which is those electric and magnetic fields. But here it's just represented by an arrow saying that that energy is propagating away from the transmit antenna and over to the receiver. Now, if you're over on the receiver side, then it's not just that signal that's out there. It's many other signals, and here they're called interferers. In addition to that, there's always some background noise level that sets a minimum on the amount of power that you must get over to the receiver to make things work. But I want you to concentrate on the fact that there are interferers here. Why? Because that's why we need bandpass filters. Now, in the block diagram that we just talked about, those bandpass filters are shown here in blocks. But in reality, they're usually created by inductors and capacitors or something similar to that. And over here on the left-hand side, you can see one of the very first receiver designs that was used in practice. This is from a British patent, I don't know the year, but early 1900s. Notice that the antenna is shown here, and then it goes into an inductor and a capacitor. Many of you know these things. That creates a resonant circuit. This actually allows the antenna to be tuned, but it also allows some selectivity, this variable capacitor. The energy in the inductor is coupled over to a second LC network or bandpass filter. And then the signal that exists between the top of that and the bottom of that is applied between the grid and the cathode of this ancient vacuum tube technology, modulating the current flow through here, and then that is developing a voltage across this LC network or bandpass filter, and so forth and so on. And every one of these bandpass filters provides a little bit more selectivity. It rejects more of the bad signals, the interferers, and allows the main signals that you want to be amplified. And there are several stages of amplification. And you'll notice that something similar is done over here. There's an amplifier here, and then there's something called a mixer. We won't go into that today, but that has to do with down converting the higher frequencies to lower frequencies, where it is then actually easier to do filters. But today's stuff, we're going to concentrate on how the filters are made. Before we can do that, however, we have to review impedances, Ohm's law, and voltage dividers. Now, again, I know that a lot of you already know some of this stuff, so bear with me or fast forward if you like. But I need to cover just a little bit of that, and I'm hoping to throw in some things that maybe you haven't thought about. Those of you who are newer to it, then this is a good primer, hopefully. All right, so Ohm's law, very quickly. You put voltage across some impedance. Now, a specific case, this could be a resistor, but in general, it could be a resistor, a capacitor, an inductor, or something else. You put voltage across it, and some current flows according to Ohm's law, which is shown by this equation here. The current, I, is equal to the voltage divided by the impedance. So the higher the impedance, the bigger the denominator, and therefore the smaller this number, and the current is lower. So more impedance means more impedance to the flow of current, less current. All right, so we're going to use this a little bit. We're also going to use another form of Ohm's law down here on the bottom, where you can take a current and force it through one of these resistor, capacitor, inductor thingies and develop a voltage across it according to this algebraic manipulation of the equation above. Basically, then what you get is a voltage, which is the current times the impedance. Impedances. All right. So a resistor has an impedance which is ideally constant with frequency. here there's a graph that shows the impedance Z. I'm just plotting magnitude, that's the vertical bars here, of an impedance. Here it's a resistor, so it's just a real number, and it's constant versus frequency, which is the horizontal axis. Except at very high frequencies. At very high frequencies, a real resistor, which you can see here, this was done from a previous video in the Nano VNA series. We measured this resistor's impedance versus frequency. And if you know about Smith charts, or if you watched that video, then maybe you can interpret what this is here. This tells us the impedance. There's a readout. It says at basically 22 ohms and 22 nanohenries in series with 22 ohms resistive. So a resistor becomes a resistor in series with an inductor at sufficiently high frequencies. And we will have to deal with that. That's part of the radio arts, is to understand how to deal with such issues. Resistors in reality are not always just simple resistors. Okay, an inductor and a capacitor, let's take a look at those. All right, an inductor has an impedance Z, which has this equation. Basically, it's proportional to frequency. The larger F is here, the larger Z will be. And the proportionality constant is the inductance itself. There's always 2 pi's floating around in the world, so the equation is actually 2 pi FL. And there's a J, and that simply is a complex number realization of the fact that an inductor, the impedance is not a real valued impedance, it is complex. What that means is the current and the voltage are out of phase. Notice on the inductor, the impedance goes up with frequency. That's the primary thing. On a capacitor, the impedance goes down with frequency, and that's because F is in the denominator. Now, just like before, we can look at these things on a Nano VNA and measure them, and I'll refer you to previous videos for that. Inductors have some non-idealities that you'll see in part 2 of this series as well. Capacitors do to a lesser extent. Okay, so with that background, let's talk about the most important circuit in all of analog electronics, according to me. I always tell the students that because this thing just appears a lot in circuit analysis. It really helps to visualize things this way. Let's say you have 2 impedances that are in series like this, and you put a voltage across those 2 series resistors. And then you look at the voltage across a single one. Here it's Z2 that we'll look at the voltage across. What you find is, according to the previous stuff, according to Ohm's law, the current is the total voltage divided by the total impedance, which is just the sum of the 2 impedances. The output voltage, according to that second equation we just looked at, is the current times that impedance, and so we get this. You do a little algebra, and you put these together, and you find out that the output voltage here is equal to the source voltage on the left times this ratio, which is a number which in general is usually less than 1, because in the denominator you have Z1 plus Z2, and the numerator you only have Z2. So why is this the most important circuit in all of analog electronics? Well, we rely on this fraction here, the voltage division fraction, to allow us to implement things that do what we want. In particular, filters. Here is a simple bandpass filter. Z1 in this case is a resistor 50 ohms. It's actually part of the internal circuitry in something like this network analyzer, or in general it could be from an antenna. Antennas have a series impedance as well. So that's Z1. Z2 is over here. It's actually a set of components in this example. A resistor, the input impedance of the network analyzer port 2, but in parallel with an inductor and a capacitor in this particular sample bandpass filter. The bandpass filter is constructed as shown in the upper right here. You can buy these boards for, I don't know, $10 or something, and that's a really good thing to do if you want to make this stuff come alive for you. You can go out and buy one of these, get one of these network analyzers, put stuff together and start trying to work with it. Now, the inductor and capacitor are these 2 elements here. I bought a small surface mount component kit and selected values according to the theory that we're going to go over, especially in part 2 of this. Here we're mainly overviewing how stuff works. But we can select values, and if we select the right values, then we will get a bandpass filter at the frequency we want and with a specific bandwidth. There's a third component here that's just a 0 ohm resistor that couples from here over to here. That's basically this line up here at the top. So you can see here a picture of the response. We'll go over this in more detail later. The blue line is the amplitude response of the filter. So it peaks at one frequency, that's the bandpass, and then it drops off in dB at higher frequencies over here and lower frequencies over here. Again, we'll go into details of this later. All right, so filters. Let's talk about how they work, and then later in part 2, how we design them. Let's start with a low-pass filter because that's the easiest filter to understand. Remember, the capacitor impedance starts out high at low frequencies and then gets very low at high frequencies. Sometimes we say that it shorts out at high frequencies. It never quite shorts out, but it gets very much smaller in value than this resistance up here, which stays constant. And so if you look at the equation, the impedance of the capacitor is in the numerator. If it's falling and the resistor is constant, the lowest the denominator can get is the value of the resistive impedance, or the resistance itself. So this is kind of, think of this as constant, but this is decreasing with frequency. And so what that does is it causes the response, V out over Vs, the transfer function, to fall off in amplitude, and that will attenuate the signals. I'm not going to go into the detail here of this for time reasons in this video, but at high frequencies, well above the cutoff frequency Fc of this low-pass filter, we get something that drops 20 dB per decade, is what we say. So at 10 times Fc, we'll be down 20 dB. At 100 times Fc, we'll be down 40 dB, and that's what this equation captures if you parse it. Now, what about this section here where it's constant? Well, that's where the capacitor impedance has become so large that it's much bigger than the resistance, and so the denominator here is dominated by Zc, so we can ignore the resistance, and we just get Zc over Zc, which is 1, and in dB that's 0 dB, so we have no attenuation there. Okay, so let's move on to a bandpass filter. In a bandpass filter, we put an inductor and a capacitor in parallel. When we do that, you can show mathematically that what you get will be a bandpass shape that looks like this. Now, how do we explain that without the mathematics? Basically, at high frequencies, this capacitor will, quote, short out, and the impedance will become very small. At low frequencies, the inductor will short out. Think of it as a wire. So at DC, it's just a wire. It has 0 resistance or 0 impedance, ideally. And so it will short out at low frequencies. It turns out, because of the mathematics that we go through in the university course, you can show very clearly that at one particular frequency, these two guys exactly cancel each other in the sense that the impedance from here to here becomes infinite. And so when that happens, ZLC is infinite, or a very large number. It dominates the resistance. So it's just ZLC in the denominator, ZLC in the numerator, and so you got 1, and so you have 0 dB. But then at higher frequencies, the capacitor is shorting out, and so the response drops off. At low frequencies, below the center frequency, the inductor shorts out and the response drops off. We're going to show in this video how you can design so that you get a desired center frequency, F0 or F0 here, but also a desired bandwidth, how wide that filter is. That's going to be the purpose of this video. It's going to be in part 2. Before we get there, however, let's take a look at what the filter looks like in practice. In practice, when we built the filter that I showed you in the picture earlier, we get a response that looks like this. It doesn't go, this is 0 dB right here where this little tiny arrow is. it doesn't go all the way to 0 dB. We have about 3 or 4 dB of loss in the filter. We're going to elaborate why that is in part 2. We also have a particular bandwidth, and hopefully we will get the bandwidth we want. But if we don't get the bandwidth we want, then we will examine some of the non-idealities of the components we talked about briefly a second ago. We'll examine that, and again, that will be shown in part 2. Before we leave part 1 here, I wanted to show some of the other things that these network analyzers, these nano VNAs, can do. The blue curve is the frequency response. This is 50 kilohertz on the left to 500 megahertz on the right. So you can see that this filter peaks right here, which in the readout is at 95 megahertz. It's designed for FM radio broadcast band. That's what we did in the class radio designs that we were working on. In addition, however, I had a viewer from one of the previous Nano VNA videos ask me about phase response. And so I included that here. That's the green line. I told this Nano VNA measuring tool to look at that. And it goes from, well, at the center, it's about 0 degrees phase shift. At low frequencies, it's close to 90 degrees, and at high frequencies, it's close to minus 90 degrees. Low frequency is dominated by the inductor. Remember, voltage and current are 90 degrees out of phase. That's what's causing this phase shift. Same thing in the capacitor, except it's in the other direction. And to go beyond that, we would need the mathematics, which we're not going to do in this video. The yellow line here is the resistance, or actually the impedance, looking into this filter. The filter is here, and we're looking into port 1, which is across these two bubbles here. That's the impedance looking in there. And we'll talk about that in part 2, like everything else, in more detail. Okay, so before we leave, I'm going to refer you to the previous videos that we've done. In particular, I'd encourage you to look at this last one here, Nano VNA Tiny SA for Radio Design. That video covers how to create a radio frequency laboratory on a budget. This is the Nano VNA. You can get these things for as cheap as 60, 70, 80 bucks. This is a spectrum analyzer, same thing. You can get them for about 100 bucks or less. And in this video, what I did was I took the spectrum analyzer and I hooked it up to an outdoor ham radio antenna and looked at the spectrum. And then we took the filter and measured its response. And then I took that antenna and fed it into the filter that I showed you just now, and took the output of the filter and fed it into the spectrum analyzer, and you can see what the filter did. This is the filter here and the response, and it was centered right in the FM broadcast band, which is this group of signals here. The stuff down here at the left in the spectrum is lower frequency shortwave signals, ham radio signals that in this case we didn't want. At the right, there's some noise coming from some lighting in the room. But after running through the filter, it got rid of all that stuff. And the only thing that was left was the FM broadcast band. That's what these filters are good for. Okay, so before we leave this part 1, I would encourage you, especially if you're new to this, to look at things like Amateur Radio Relay League publications. In addition, I want to make a point that you cannot transmit, you can't create radio transmitters just willy-nilly. You have to be licensed to operate, because otherwise you're going to interfere with people and you're going to get in trouble. So don't do that. Instead, go ahead and get an amateur radio license if you don't already have one maybe. But just be attentive to the rules. If you want to look at more detail on things, then you might want to go out to the website, just search for ARRL, A-R-R-L, and go to their website, and they have lots of training material. You can buy books. The books are written by people who, they started out as amateur radio operators, but they ended up making careers out of this, which is basically what I did as well. And then they share that. That's what I'm hoping is done here. Coming in part 2, we will look at quality factor. That's the way that we design the filter for the bandwidth we want. In the FM broadcast band, we want something centered around 98 megahertz and about 20 megahertz wide, because that'll cover all the FM broadcast channels, and then we can reject everything lower and higher in frequency. So that's what we'll talk about there. We'll do some design examples. We'll talk about impedance matching, and then also higher order filter design. And by the time we're done with that, you will know everything that professional designers know. Maybe not in as much depth. You know, they have the 10,000 hours plus of experience that's required to be an expert, but I'm hoping that we will be able to show at least a good flavor of everything that is needed and allow you then to, for example, build things and try them out. Again, don't transmit without having a license. Be careful what you're doing in all cases. But I'm hoping to illuminate design. Thank you for watching, and please check out some of the other videos. And if you're up for it and you want more depth, then look at part 2 of this one. Thanks again.